Cycling, Sports Thematic Unit. Bicycles were invented during the first half of the 19th century. Initially, they were foot-propelled devices with two wheels, usually made out of wood and metal, just as wagon wheels would have been made out of. But as the 19th century progressed, various innovations were added to develop bicycles to be what they are today, such as pedals and cranks were added so that instead of pushing your feet against the ground, you pedaled. Chain drive was added so that the pedaling action, instead of moving the front wheel, was transmitted by chain to the back wheel. And later in the 19th century, pneumatic tires were developed. And all throughout the 19th century, it was found that this was a fast, relatively inexpensive, somewhat safe, compact in terms of being able to take your bicycle relatively easily anywhere, mode of transportation, at least compared to walking. And you have to remember that even in the 19th century, one of the key modes of transportation was walking. But of course, you needed suitable road surfaces over which to travel on the bicycles. In the 20th century, the use of bicycles has exploded, and even more so in the 21st century, where riding surfaces and in fact riding paths and lanes dedicated specifically for bicycles are available in countries all around the world. In this lecture, we'll have a look at some of the interesting physics associated with bicycles and bicycle ridings. Here you see a typical road bicycle with parts including the saddle, the frame of the bicycle, the cranks and chain rings that you push with the pedals, the chain connected then to the cassette and gears on the back wheel, the derailleur that allows you to change the location of the chain and choose which sprocket on the cassette the chain is riding on. In fact, there's also a front derailleur in the case where you have more than one chain ring to allow you to choose between a larger or smaller chain ring. Of course, there are wheels, and then to slow you down, there are brakes and brake levers and shifting levers that are used to control all of these things. Well, of course, to get going, you push on the pedals with your feet. That turns the chain ring, which then causes the chain to move, which puts a tension on the chain, exerting a force on one of the sprockets in the cassette and the back wheel, which in turn causes the wheel to rotate. But let's look at this in a little more detail, and in particular think about the lengths of the crank, the diameter of the chain ring, the diameter of the sprocket on the back wheel, and the diameter of the wheel, and think about the relationship between the instantaneous force of your feet on the pedals and how that transmits into a force of the back wheel on the road. So if you're applying a force on the pedals, and just for simplicity's sake, let's suppose that the crank arm is horizontal as shown in the picture, and then you're standing on the pedals, so the force is in the downward direction. And so in this case, there's a torque then on the chain ring that the crank is attached to. That's just given by the distance from the axle in the bottom bracket that the cranks and chain ring are attached to the location of the axle for the pedal. And so the force of your foot downwards on the pedal times the distance from the middle of the chain ring to the pedal axle is the torque that your foot is inducing on the chain ring and crank assembly. That torque causes a torque on the chain ring, which is of a smaller diameter or smaller radius than the crank arm, to induce a force on the chain and therefore a tension in the chain. But the crank arm and chainring assembly is all one rigid assembly, so the torque that you're applying through the pedal and crank is equal to the torque on the chainring, and hence then the force on the chain, where the force on the chain times the radius of the chainring will be equal to that torque that I've called torque sub chain in the equation, and that has to be equal to torque sub pedal. And so this tells us that the force on the chain, and hence the tension in the chain as you push on the pedal in this scenario, is equal to the force on the pedal times the radius of the pedal, by which again I mean the distance from the center of the chainring to the pedal axle, divided by the radius of the chainring. And as you can see from the picture, the term that I call R pedal is bigger than the term R chain, and so the force on the chain is going to be larger than the force you're putting on the pedal. So that tension in the chain then translates into a force on the sprocket attached to the back wheel. And so again, there's a torque on that sprocket, which is equal to torque on the wheel, and we can carry out the same kind of calculation as you see in the top equation, which means the force on the chain, or the tension in the chain that causes a force on the sprocket, times the radius of the sprocket will be equal to the radius of the wheel times the force that the wheel imparts onto the ground. And in particular, the force of the wheel on the ground is equal to the tension in the chain, or the force of the chain onto the sprocket, times the radius of the sprocket divided by the radius of the wheel. And here, the radius of the sprocket, as you can see, is much smaller than the radius of the wheel, and so the force of the wheel onto the ground is going to be much smaller than the force of the chain onto the sprocket. Now, combining this with the equation on the previous slide, then we can relate the force on the pedal to the force of the wheel on the ground, and that's given in the bottom equation, where it's equal to the radius of the pedal, that distance from the center of the chainring to the pedal axle, divided by the radius of the chainring, times the radius of the sprocket, divided by the radius of the wheel. And for typical road bicycles in general, I think in the 21st century, the ratio of sprocket to wheel is much less than 1, and the multiplication of the ratio of the sprocket radius to the wheel radius times the radius of the pedal to the radius of the chain, that second number is larger than 1, results in an overall number that's quite a bit smaller than 1, which tells you that the force of the wheel on the road is smaller than the force of your foot on the pedal. However, there are two, or at least a couple of reasons why you want to set it up this way. First of all, the force of your foot on the pedal, if that translated to the same force of the wheel on the road, would likely cause the wheel to spin, because the friction between the wheel and the road wouldn't be large enough to cause the wheel to move forward instead of just spinning in place. Secondly, it causes more travel in terms of the circumference of the wheel per revolution of the cranks. And so your feet travel in the circle that the pedals describe a much smaller distance than the wheel travels, and hence the bicycle moves forward. And it's kind of the opposite from what happens in the case of a pulley system, where a multi-pulley system, the object is normally to be able to apply a smaller force to move an object that has a larger weight. And the way you do that, or the trade-off by doing that, is that then you have to move the rope that's ultimately pulling the pulley system and the object up into the air much further than the object is actually raised. Here it's kind of the opposite. You have a larger force that you're imparting to the pedals than is transmitted to force of wheel on the road, but you travel a much further distance on the bicycle than the distance your feet travel around on the pedals. Now, although many bikes just have a single sprocket at the back and a single chainring at the front, then of course many other bikes have multiple gears that can be selected with many different sprockets at the back that can be selected by adjusting a rear derailleur, and with 2 or even 3 chainrings at the front that can be selected by moving a front derailleur. And this allows the rider to have different combinations of size of front chainring coupled to back sprocket on the back wheel. And what this means in one sense is that the relationship between the force that your feet are applying to the pedals will vary in terms of the force then transmitted by the back wheel to the road, depending on the ratio of selected sprocket and chainring. A different way again to think about it is by adjusting that gearing, the number of times you have to turn the front pedals to correspond to some other number of turns of the back wheel will change as a function of the ratio of front chainring size to back sprocket size. Now, of course, if you look at these things and the way mechanically that they operate, there are of course teeth on the chainrings and sprockets, and the chain itself has holes in it where the teeth fit into, and so everything is discretized. And for many people, thinking about the relationship between the gearing of their bicycle and its operation and motion, they just think in terms of numbers of teeth, since the teeth are standardized on many bicycles, and at the very least, the teeth on the front have to correspond roughly to the teeth in the back because they both need to fit into the same holes in the chain. And you can work out the speed of your bicycle for a given cadence, a different angular speed of the pedals going around, as long as you know the circumference of your wheel, which just depends on the diameter of the wheel, and then the ratio of the number of teeth in the chainring you're using to the number of teeth on the sprocket that you're using. So let's have a look at an example of gearing. And suppose we've got a rider with a road bike that has wheels with diameter 670 millimeters. So that's a typical size for wheels, and the particular details depend on the type of tires chosen and how much they're inflated and so on. And let's suppose our rider is spinning the cranks at a rate of 90 revolutions per minute and is using a 52-tooth chainring and a 17-tooth sprocket. So first, let's change the cadence to revolutions per hour. So that's 90 times 60, or 5,400 revolutions per hour. Then let's change the wheel circumference to put it in kilograms. So the relationship between the circumference of the wheel and its diameter is that the circumference is just pi times the diameter. And here we've changed the diameter to meters by divided by 1,000, and then to kilometers by dividing by another 1,000, as you see in the ratio in the first part of that second purple equation. And then calculating the numbers, this turns out to be 0.0021 kilometers. So that's just the distance around the outer edge of the tire. Now finally, we can apply that formula on the previous slide that tells us that the speed will be equal to the cadence, 5,400 revolutions per hour, times the wheel circumference, 0.0021 kilometers, and then times the ratio of chainring teeth to sprocket teeth, 52 divided by 17. And putting it all together, we find that then the rider will be riding at about 34.7 kilometers per hour. And of course, we changed the units for the cadence, so we'd end up with something per hour, and we changed the wheel circumference, so we'd end up with something in kilometers, so that our final speed would be in units that are commonly used, kilometers per hour. Now you can see that if the rider increases the cadence, the rate at which they're turning the pedals, of course, their speed will increase. And similarly, if they went to a smaller number of sprocket teeth on the rear wheel, that their speed would increase at the same cadence. Or conversely, 52 teeth tends to be a bigger chain ring. If they went to a smaller chain ring with 39 or 36 or 34 teeth, then that changes the numerator, which means their speed would decrease for the same cadence. And then, of course, if someone has their tires less inflated than someone else, this will make a small difference because of the small change in wheel circumference. There are other types of bicycles that just have smaller, quite a bit smaller diameter and hence circumference wheels, like children's bikes or bicycles for junior racers, etc. But as you can see, using this simple formula, it's very convenient to be able to determine at what speed you'll move on your bicycle, as long as you know at what rate you turn the pedals and what gearing you decide to choose. Now, when you're riding along, you have to continuously apply force to the pedals. That translates into a force of the wheel on the road, which should accelerate you according to Newton's law F equals ma. But of course, you have to keep pedaling, and if you stop pedaling, you will slow down and eventually stop. And so this means, of course, that there are forces opposing the motion of you riding forward on your bicycle. And the three key ones are the rolling resistance, which, if you're on a flat road, is approximately given by this constant C sub r, which is just called the coefficient of rolling resistance. It has to be measured for the kinds of surfaces in contact and the area of contact between the two surfaces, in this case between the bottom of your wheel and the road, and then times the mass of the rider plus bicycle, and then g, the acceleration owing to gravity. Now again, that's for the case of riding along a flat road. If you're on a hill, then the rolling resistance also has a factor of cosine theta multiplying it, where theta is just the angle between horizontal and the slope of the hill. The second and typically more important force that's resisting your motion is air resistance, and this goes like 1/2 times C sub d, where C sub d is the drag coefficient, which depends on the geometry of the object, times A, the cross-sectional area of the rider and bike as it passes through the air, rho, the density of the fluid, which in this case is the air, so air density, and then finally the square of the velocity of the rider with respect to static air. Of course, if there's a wind blowing, then the velocity has to be the relative motion of the rider with respect to the air, and so also factor in the direction and speed of the wind. And then the third main factor that resists your bicycling motion can be gravity in the case that you're traveling uphill, and there the gravitational force will be equal to the mass of the rider plus bicycle times acceleration owing to gravity, and then times the sine of theta, where again theta is the angle between the slope and horizontal. So the force of your feet on the pedals and hence of the wheel on the ground tending to want to accelerate you forward is offset by the forces of rolling resistance, air resistance, and of traveling uphill, gravity. And so if you're just wanting to travel at a constant speed, these forces need to balance out. Now, the force of gravity just depends on the angle of the slope you're on, and the rolling resistance, although it does depend and is potentially decreased a little if you're on a slope, to first order is more or less constant and just dependent on the properties of your tires and the surface you're riding on. Whereas the air resistance changes like the square of the speed that you're traveling. And so on a flat road, above sort of 10 or 12 kilometers an hour or so, it's really air resistance that totally dominates. And by the time you get up to 20 to 30 kilometers an hour, it can be more than an order of magnitude bigger effect, the air resistance, than the rolling resistance. And so even for recreational riders who typically are going to ride at over 20 kilometers an hour, it's really the air resistance that is what's requiring you to constantly put the force onto the pedals. And this becomes worse and worse, or harder and harder, as you want to increase the speed of your bicycle, and it goes like the square. That additional force you have to apply is changing like the square of your velocity. So if you've ridden in bicycle races or you've watched professionals racing, you see that they always race in a tight pack called the peloton. And even if a few of the riders are off the front in a breakaway, they're usually in a long line or an angled line if there's a crosswind. And of course the idea there is that they're trying to minimize that force of air resistance by having someone in front of them blocking much of the air or pushing much of the air out of the way so that much less of it impacts their riding. And in single file, if you're tucked up close to the rider in front of you, you can save up to 20% or so in terms of the drag effect. For riders in the middle and back part of the peloton, they can be saving even much more than that in terms of the energy they have to put out to overcome what for them is the much reduced air resistance compared to the riders right at the front of the peloton. Although in some cases, cyclists would like to minimize the rolling resistance that causes them to slow down, for many situations, the speed of the bicycle and rider is high enough that the rolling resistance really isn't the main effect. On the other hand, when trying to control your bicycle, to ride around corners, to travel across rough surfaces, it's very important that the friction between the wheel and the road prevents you from sliding, from crashing. And so different types of bicycles employ different types of wheel sizes and tire sizes to really adjust the handling that your bicycle will have on different terrain, different conditions, and particularly when cornering. And so you see in the three photos on the far left, mountain bike tire. This is something like a 2.2 inch, which is an older but relatively recent standard type width of the tire on a so-called 29er wheel. And you see that it's also got a roughness to it, so it's got features on the surface. And of course, for that bike, it's used for trail riding. So you're riding over dirt and gravel, maybe grass, roots, rock, could be muddy so that it's wet, slippery surfaces, etc. And to corner or descend or just generally stay on top of your bicycle when doing that kind of trail riding, it's essential that you have a better contact surface area and a rougher surface in contact with the ground to be able to stay upright and to maneuver your bicycle. There's a kind of racing that is particularly popular in Western Europe called cyclocross racing, but is also becoming popular in other parts of the world. And there you typically race on a 3 kilometer or so long track that's over sand and mud and gravel and dirt and grass. And so it's not quite as demanding as some of the really technical trails that you would take a mountain bike on, but it's much rougher, harsher, and has very sharp cornering, usually designed into the course, than for a road bike. And so the wheel you see in the middle has also a tire that has rough features on it, and is again a bit wider than the wheel at the right. The wheel at the right and tire is for a time trial bike, in fact. And so there is some effort to try to design for minimizing rolling resistance. Some tires are designed particularly for wet weather. The ones you see here are designed for sort of all season, but more along the lines of a dry, smooth road surface. And so they'll provide the right amount of traction for cornering in those conditions, but will provide reduced traction if the road surface is wet or covered with sand, etc. In addition to the size of the tire pressure is also varied depending on the types of surfaces and conditions in which you're riding. And so again, for the mountain bike tires on the left, to get a really good contact area between the tire and the trail surface, they're usually operated at quite low pressures, even down as low as 20 to 25 psi. In the case of trail riding, if you're riding in regions with lots of rocks and roots, etc., of course you want to avoid getting a flat tire, and so you are usually trying to balance between the maximal contact area between your tire and the surface you're riding on versus not having so little pressure that if you hit a bump with enough force, the tire will collapse and potentially puncture. In the case of cyclocross tire pressures, there, at least the professionals, ride at very low pressures, something like 20, 18 psi or so, or to translate into SI units, it's a little over 1 bar or a little more than atmospheric pressure. There, again, you're trying to maximize the traction, especially when trying to go around the very sharp corners designed into the courses. But the courses don't have the kind of roughness or sharp obstacles that you might find on a trail course in mountain biking. And then in the case of the time trial bike on the right, there the tire pressures tend to be quite high, maybe 100 psi or higher. And there again, the idea is that the tire is designed to be operated at those pressures on dry, smooth road conditions and still be able to corner at high speeds. And at that pressure, it also allows the rider to have minimized the rolling resistance. Of course, it's great to go fast on your bicycle, whatever type it is and on whatever terrain, but at some point you need to stop, and either because you're finished your ride or there's an obstacle ahead, or if you're riding downhill, you need to control your speed. And so, of course, stopping or slowing down is affected by the use of brakes. There are a number of different designs of brakes used on bicycles. The main principle of operation is that you're trying to bring some surface into contact with either the wheel or something attached to the wheel to create friction to slow down the turning of the wheel. On the picture in the bottom left, you see a typical kind of caliper brake system. And what happens there is you pull the lever on the handlebars. This pulls a wire that's housed in the black cable, like the one you can see in the top right of that picture, that runs down to the calipers at the wheel. Pulling on the lever pulls the wire, which causes the calipers to squeeze closed, which causes the pads at the end of the brakes to come into contact with the rim, and then it's that friction between the brake pads and the rim that starts to slow you down. The other main type of brake used is a hydraulic disc brake, as pictured on the right. Here again, there's a lever usually up on the handlebars, but instead of a mechanical cable, although some disc brakes do use mechanical cables, but instead many use a hydraulic fluid, and so engaging the lever pushes the hydraulic fluid, the pressure in the fluid wants to stay the same everywhere, so changing the pressure at the top gets transmitted all the way down to the bottom, and so the fluid presses on the cylinder in the hydraulic disc brake itself, as you see is the black part attached to the forks, and that causes pads to squeeze onto the rotor, which is pointed out as the silver disc-shaped object. And there again, it's the friction between the pads and the rotor that then causes the wheel to slow down. Now, I think for many decades, the predominant method for road bikes was the caliper brakes, as pictured on the left. There are different mechanical versions of those called V-brakes and other brakes. Of course, there's some kinds of children's bikes where the brakes are actually housed in the unit that the cranks are attached to at the bottom bracket. I don't want to go into the details of those, but hydraulic disc brakes have become increasingly popular, first on mountain bikes and now also on different types of road bikes. One of the big advantages of disc brakes is that their performance, their stopping power, is not affected very much by wet weather. Another advantage that is not so important for most recreational riders, but for people in situations where they're riding down long and twisting and turning descents, the constant braking will heat the rim and potentially cause a problem for your tire, whereas the heating in the case of a disc brake is all onto the rotor, and so it doesn't affect the wheel or tire at all to first order. Some of the disadvantages potentially of disc brakes are, at least up till now, they've tended to be heavier than comparable levels of models of caliper brakes. And in the case of hydraulic disc brakes versus mechanical caliper rim brakes, the hydraulic components can require potentially a little more maintenance, or maintenance that's perhaps a little more time consuming than the case of a mechanical braking system. Now, as I said on the previous slide, one of the things that can resist your forward bicycle motion is just the effect of gravity as you ride up a hill. And so let's have a look at riding up a hill in the case of a pro cyclist, or maybe you're a cyclist that can generate 300 watts of power, which many recreational cyclists can do that. And we'll think here in terms of the power generated by the cyclist instead of the force of the feet on the pedals and the wheel on the road. And so for pro cyclists, I think it's relatively easy, I would say, for them to generate 300 watts of power continuously over a period of an hour. And so then what we want to think about in this example is if they're doing that while they're riding up a hill that's 10 kilometers of riding distance long with a constant gradient of 8%, and in this simple case, we choose to ignore rolling and air resistance, and if the rider is 70 kilograms, then how long will it take the rider to get to the top of the hill? So remember that road gradients are defined as the rise, the vertical distance change, divided by the run, the horizontal distance change on the hill, and then times 100 to turn it into a percentage. So the picture on the left just shows you what I've defined as L, the actual riding distance along the hill, H, the vertical height of the hill, and D, the horizontal distance that's traveled. And in that right angle triangle, of course, the square of the riding distance L is equal to the sum of the squares of the horizontal distance plus the vertical distance squared. And then the definition of gradient tells us then that the relationship between the height is that it's equal to 0.08 times the horizontal distance. And then using the first equation, this means that the height of the hill is equal to L divided by the square root of 1 plus 1 divided by 0.08 squared. So all I've done there is combine the first two equations. L squared equals d squared plus h squared, and h equals 0.08 times d, to eliminate d and then rewrite h in terms of L and those constants. And so for this example, putting in the L equals 10 kilometers term tells us that the height of this hill is 0.797 kilometers approximately, so a little bit less than 1 kilometer tall. Now, remembering that the change in gravitational potential energy goes like mass times acceleration owing to gravity times the height change, or mgh here, then this rider will need to expend E equals mgh equals, and here I'm ignoring the weight of the bicycle and just using the mass of the rider. And so that's mgh, 70 kilograms times 9.8 meters per second squared times 797 meters, or 0.797 kilometers. But transferring to meters will give me a number in joules, so it's 547 kilojoules of energy needed to go from the bottom of this hill to the top of the hill, just to offset the effect of gravity. Now, we're told that the cyclist could maintain a power output of 300 watts for an hour, so we're going to see if this rider can get to the top of the hill using that power output. Remember that power is just energy divided by time. Here we want to rewrite to find the time, so that's going to be energy divided by power. And so the energy needed, again, is 547,000 joules. The rider is generating 300 joules per second, or 300 watts of power. And so that ratio turns out to equal approximately 1,820 seconds, or converting to minutes, 30.3 minutes. And so that's much less than an hour. So in this scenario, our rider will be able to maintain that power output all the way to the top and climb this 10 kilometer, 8% gradient hill in about 30 minutes. And I must say that's a lot faster than I can ride that type of hill. And I always find it very impressive, the power outputs that the pro cyclists can maintain for very extended periods of time. So now we turn to a quite interesting aspect of bicycle riding, and one that's been, I think, misunderstood for a long period of time. And probably still all of the details aren't perfectly understood even now. And that's the simple fact that humans can ride bicycles, can balance bicycles, and in particular that it's relatively easy with a little bit of practice to balance a bicycle that's moving, and even a little easier when moving a bit faster, compared to moving at slow speed, and in fact it becomes quite hard when the bicycle is stationary to stay upright. So what's happening? Why is it relatively easy to stay upright when moving, but extremely difficult to do so without a lot of practice when not moving? Now, as the wheels turn, of course, they have angular momentum. They have rotational inertia associated with them. And we'll talk about that in a little more detail with a toy example on the next slide. But as we know, objects that have angular momentum is conserved, and an outside torque has to be acting on the object for its direction of angular momentum to change. And so an old idea was that it's easy to ride a bicycle when it's moving, but hard when it's stationary, because the angular momentum in the wheels resists falling over because you require a torque to change the direction of the angular momentum, which points out from the plane of the wheel. And so that's sort of a convenient idea that fits roughly with physics we know about, but of course, as it turns out, that's not really the answer, and it can be shown that that is only a small factor in the overall stability of bicycles. And of course, it's not just the stability of bicycles when trying to ride them. You can take your bicycle with no rider on it and push it, and it's relatively easy to get it to move along without falling over on two wheels and stay upright. So what's happening? What are the factors that matter? Well, there are a number of different things. The mass distribution of the bicycle and the rider on the bicycle matter. The geometry of the frame and the angles of the fork and location of the wheel with respect to the handlebars and etc. are all important. There are gyroscopic effects associated with the angular momentum of the wheels that can play an important role. But I think to first order, it really just comes down to steering, both the steering actively by the rider, but also potentially self-steering effects of the bicycle itself. Especially in the case where you do this experiment, as I suggested, and you just push the bicycle and have it rolling along with no rider, and you'll see that it can quite easily stay upright until it slows down. So just for fun, let's have a look at the wheel angular momentum and think about the difficulty in having that angular momentum change direction. Can this really provide a key component to the stability, that's that resisting of the angular momentum, the change in direction, and hence the tilting of the bicycle? So let's ask the question, what torque would be required to change the angular momentum direction of a 1 kilogram wheel that has a diameter of 670 millimeters by 60 degrees, and all the while the wheel moving forward at a constant speed of 20 kilometers per hour, and that this change occurring from upright to falling over to a 60 degree angle with respect to upright occurring in 1 second. Well, there are a number of different things that we need to do in this calculation. The picture on the left is just a cartoon of the original direction of angular momentum, the horizontal purple line, compared to the direction 1 second after it starts tilting, so that it's now at a 60 degree angle. And then finally, the difference between the final and initial angular momentum directions given by the red line. Now, of course, a 60 degree tilt is a huge tilt, and almost certainly you're falling over and going to crash. So this is quite extreme. But all I'm trying to do here is just to give a sense of the size of the torque needed to effect a change like this. And in doing so, get a sense of whether the torque needed to change the angular momentum, or more generically, is the angular momentum of the wheel really contributing much to the overall stability of the bicycle. So let's assume that all the mass of the wheel is at the edge, and that just means that the rotational inertia I is going to be equal to the mass of the wheel times its radius squared. If we assume that some of the mass, some of that 1 kilograms is close to the center, that's only going to decrease the rotational inertia and hence decrease the angular momentum of the wheel. So this is kind of a conservative estimate. Angular momentum is equal to the rotational inertia times the angular speed. So we need to calculate the angular speed. That's usually given the symbol omega, and that's equal to, in this case, 2 pi times the speed divided of the bicycle divided by the wheel circumference. And then combining that rotational inertia I and angular speed omega and that will allow us to calculate the magnitude of the angular momentum, L. And that in turn will tell us what kind of torque is needed to change the angular momentum by the amount suggested and in a time of 1 second. So this problem, let's work in meters, seconds, and kilograms. So we'll change any of the units, any of the pieces of information that are given in different units than those. And then the reason I picked 60 degrees is actually just to simplify the problem. And although in principle it's a vector problem, the fact that it's a 60-degree change in the angle, but with the speed remaining constant, means that the difference in between the final angular momentum and the original angular momentum is just going to be the change in direction, given by, again, that red line in the diagram. But that diagram is, because of the 60 degrees, an equilateral triangle, because the length of the two purple vectors has to be the same because the speed hasn't changed, and so only the direction of the angular momentum vector has changed. And that means that that red vector has the same length as the two purple vectors because it's an equilateral triangle. And that means the change in the angular momentum, the magnitude of the change in angular momentum, is just equal to the magnitude of the angular momentum from the outset. And so that was just a convenience to pick this extreme angle of 60 degrees because it makes the geometry simple. So then to calculate the torque, it's going to be equal to the magnitude of the change of the angular momentum, which in this particular geometry and constant continuous speed of the bicycle case is just equal to the magnitude of the original angular momentum. And that's equal to m, the mass of the wheel, times the radius of the wheel squared, times 2 pi, times the speed of the bicycle, divided by the wheel circumference, and then divided by the time change. And so putting in the numbers, that's 1 kilogram times 0.335 meters squared times 2 pi times 20,000 meters per hour, but converted to seconds with the factor of 3,600 in the numerator, and then divided by the wheel circumference is just pi times its diameter, so pi times 0.670 meters, and then divided by the time change, 1 second. And putting that all together, I find that the torque needed to affect this change in the angular momentum of this wheel is a little less than 2 Newton meters. Now, if you think about that, if you held a mass in your hand of 0.2 kilograms straight out from your body, and if you assume that you're holding it approximately a meter from the pivot point, then that 0.2 kilogram mass is going to be exerting a torque that's at a similar level as this 1.9 Newton meters. So thinking about yourself on the bicycle and your position, or thinking about riding and putting your hand out to signal a turn, etc., you're shifting masses around on the bicycle that can easily be inducing torques to the right or the left to try to tilt the bicycle that are easily greater than 2 Newton meters. And in this case, the 2 Newton meters, okay, you've got 2 wheels and we only did the calculation for 1, but still, it's not very much torque that's needed to cause the bicycle to start tilting by quite a large angle and potentially fall over. And so this very simplistic calculation is still, I think, illustrative of the fact that it really can't be the angular momentum in itself that is the key factor in the stability of the bicycle when moving. So again, that calculation on the previous slide was pretty simplistic in terms of trying to model aspects of really riding a bicycle. But what is it that really gives rise to stability of bicycle, either with a rider on it moving along, or even, as I said, with the bicycle just pushed with no rider? And if you try it yourself, you'll see that you can easily get the bicycle to roll along and it won't fall over until it gets to relatively low speed, assuming it's on a smooth, flat surface. So it turns out that there are a combination of effects that combine together to contribute to the stability of a bicycle when moving. But it comes down to first order, I think this key factor that as the bike starts to lean, because the front wheel is allowed to turn on the pivot at the front of the frame called the headset, that as the bike starts to lean in one direction, this tends to cause the wheel to steer in that direction. But the very act of the front wheel steering in the direction that it's leaning causes the bike to then want to tilt in the opposite direction. And so in this case where you push a riderless bike and let it roll along, especially as it gets to lower speeds, but still not so slow that it becomes unstable, you can even detect this wobble back and forth of the bike starting to fall in one direction, the steering turning, and that causing it to then start leaning in the other direction. And it's this sort of self-correcting effect of the steering of the front wheel that's a key aspect of the inherent stability. And scientists have shown that if you then lock the steering of the front wheel, it will basically fall over as fast as a bicycle will fall over that's not moving and that you let go very quickly. Whereas if you don't lock the steering, you can push the bicycle and it can roll along for a substantial period of time on a flat, smooth surface until it starts to slow down. Now, of course, if you've got a rider on the bicycle, there's not just this sort of self-steering effect that can occur, but the rider will actively be steering the bicycle themselves. Now, if you've seen a younger person or anyone new to cycling first start to ride a bicycle, you'll see that they seem very unstable, and to inexperienced bicycle riders, it always looks a bit surprising that they find it so difficult to stay upright initially. And I think there are a couple of effects that are in play there, or probably many effects, but a couple ones that can be identified are that, first of all, when initially learning to ride, people tend to start learning at very low speeds. And so this means that the steering that they have to effect to correct for tilts in the bicycle by losing their balance are much larger, because the steering changes needed at low speeds have to be larger angle to correct for the lean compared to the steering angle changes needed at higher speeds. And so for new riders learning how to ride, they're wanting to do it at low speed, but this means they have to have larger corrections to the steering angle to correct for imbalance and leaning. And naturally, they haven't learned how to do that without some practice, and they'll tend to oversteer or understeer and not quite correct for the lean. If you can get those learning riders to get going faster, then you see that they immediately find it much easier to control the bicycle, especially if they're able to prevent themselves from trying to oversteer, which will exacerbate the problem, and are able to do smaller corrections to the steering. And then in general, higher speed riding is inherently more stable because the corrections needed are smaller, more subtle, and easier to manage than the large corrections needed at lower speed. Now, scientists have built experiments where they have a bicycle-like device where the angular momentum of the wheels is canceled out by wheels of the same rotational inertia and angular speed, but rotating opposite directions. And they find that this has not very much effect on the overall stability of a bike, whether it's got a rider on it or is riderless. And so one of the interesting conclusions of this discussion of riding stability is that it can be tempting in some situations to try to apply very simple physics concepts to a system and predict outcomes or explain behaviors based on it. And while sometimes that ends up being correct, as we've seen in a situation such as with a bicycle, it actually can give you quite a misleading result. And if you just look into things a little deeper, you start to see pretty quickly that your simple explanation based on the surface simple physics phenomenon isn't really what's going on. And a deeper analysis can show you more correctly what's happening. It's still physics that's governing the behavior of the system, like the rider riding a bicycle or even a pushed riderless bicycle. But even the description I've given you is really just approximate, and the details are quite a bit more complicated. And the reality is that modeling the riding of a bicycle and its stability is something that's a quite complicated problem to tackle, even from the point of physics. Well, to summarize then, I have to say that I find bicycles to be amazing tools and devices for recreation and sport, but also amazing because they really rely on a host of different physical principles in their operation. We talked about aerodynamics and rolling resistance and their relationship to the effort needed to keep a bicycle moving. We've discussed the power that a cyclist transmits to the back wheel through the force in the pedals, but also power in a more general way in terms of moving a bicycle up a hill. We've discussed the advantages of gearing and being able to select different gear ratios on the bicycle and the relationship between those gear ratios and the rate at which the pedals are turning to the speed that the bicycle will go. We discussed how braking is affected and that really just friction is used by squeezing braking surfaces either on to the rim of the bicycle wheels or onto rotors attached to the bicycle wheels. And then finally we had an interesting look at the stability of bicycle riding and even the stability of a moving riderless bicycle, and how this is, as it turns out, quite complicated to analyze with physics and a little different than what our simple physics intuition might have caused us to guess. Well, bicycles, again, are truly incredible devices, and a lot more could be said about them. One could talk about the material components used and those material properties: carbon fiber, aluminum, steel, titanium. We could discuss how frame geometries are designed and determined and how they differ for different types of bicycles and riding styles. A whole discussion on suspension systems could be carried out, and this is particularly important in the case of mountain bikes and riding over rough roads. In talking about the force transmitted to pedals, we took sort of a simplistic case of pressing downwards when the pedals are horizontal, but of course you can transmit much more power on average to the back wheel if you're able to put force on the pedals as they go all the way around in their circular motion. This is partly helped in the 21st century by clipless pedals that were first introduced in the middle of the second half of the 20th century. Before that, people that wanted to get more efficient in pedaling used toe clips. But here, the sort of attaching of the shoes to the pedals through the use of clipless pedals or toe clips allows you to apply a force almost all the way around through the pedaling motion. And then, of course, a lot could be said about the biomechanics of the rider in riding the bicycle and controlling the bicycle in different riding positions and the aerodynamics associated with different bicycle shapes and geometries and rider positions.